Thank you very much for this nice introduction. Actually, my talk is a bit around the problem you might face when you run out of space, or when you ever had the problem that your hard disk is full, or you have an MP3 player, back in the 90s or 2000s when you had an MP3 player and you were like, yeah, I want to add this song, but actually, oh no, I don't have capacity left. And I think every database administrator knows the situation when your MySQL cluster, or even if you don't have a cluster, your hard disk runs full, and you are faced with the situation that you need more space. And this brings me to the title of my talk, which is why Ricardo, the company I work for, choose Bigtable to complement BigQuery. Let me tell you a bit about Ricardo if you don't know it. It's a web auctioning site that is online since almost 20 years. So it was founded in 1999, and it's giving secondhand a new home. So 2/3 of its inventory is actually secondhand stuff, and 1/3 is around new stuff. And you can get stuff via an auction or a fixed price offer. As you can see here, it's various things. Right now, of course, my main interest is bicycles, so that's why you see a lot of bicycles that are recommended to me. Again, my name is Tobias Kaymak, and I work in the data intelligence team at Ricardo. So that means I'm responsible as a data engineer for ensuring that everything that happens on the platform can be analyzed and can be basically made into something actionable by analysts and other business leaders. That brings me to the setup. So how does Ricardo's current data processing setup looks like? So Ricardo moved to GCP, or to the cloud, fully in 2019. And with that, we got a bunch of new technologies. So some of them might be familiar to you if you have been around the GCP universe. For example, Google BigQuery, you might already know. It's a cloud data warehouse. It speaks SQL, so you can basically say, I know SQL, so I know how to use BigQuery, because it consists of tables that are then just created inside of different data sets. And as soon as you have these tables, you can start analyzing your data. It can range from terabytes to petabytes. And you don't need to manage any servers or infrastructure to actually benefit from the data warehouse. How do we get the data from our production systems into BigQuery? Well, we have Kafka, which you might know is a message queue. All the teams are sending around 39 different Kafka topics towards our Flink cluster, which is a stream processing framework that is executing Apache Beam pipelines that are basically doing only one job. They are reading the Kafka topic in a meaningful way, transforming this, and then inserting that into BigQuery so that we can analyze the thing. Apache Beam is not the main topic of this talk, but you can think about it as a unified programming model to actually do batch and stream processing in one go. So you don't need to basically write different pipelines for different use cases. You have one framework that can deal with both use cases so that you can save time while developing. That brings me to my problem. And my problem, again, is about data, or how to make sense out of data. And if you have ever been in the SQL world, you might know the following query. So when you just want to join two different tables together, in our case, it is articles and assets. And articles are basically the articles that are online on our platform, and assets are the descriptions of these articles that can be in German, in French, or in Italian, which are the main languages of our platform. And these are stored for historical reasons in different tables. You might ask yourself why, and then I can answer you. Ricardo is from 1999, so there are some decisions made back then that have been just set into stone for now and are hard to change, so we have to live with it in the DI team. So as you can see here, again, if you want to make sense out of an article that was online on the platform, for a specific amount of time, at a specific point in time, you need to join in the assets table, because people, of course, can upgrade or update the description of an article. So if you were selling something like a motorcycle and then you think about, I forgot to mention that the right handle has some problem, I'm just going to update the description. That actually is reflected then in the assets table. And a simple join here is a select star. Of course, select star is something you should avoid when running on BigQuery, because it's a columnar data store, but for the simplicity of the example, we just keep it like this. And if you then join articles and assets together, you might join them on the article ID in this case. So that's basically a very simple thing to then combine both tables together. That's a batch use case. And the standard use case, again, you might face when the data is already in BigQuery. The main concept I want to bring across is that a stream for us is just a table in motion, and a table is a stream at rest. So that means there's a one-to-one mapping between a table and a stream in Kafka. So that means that a table has a schema and a stream should also have a schema to make sense out of it. That also means that if you can join two tables, you should also be able to join two streams together, right? And as you might know, in BigQuery, you pay for the amount of bytes you scan. That means that the less you scan, the more money you save, or the less money you pay. And since an article can be online on the platform for quite some time, as you know, we are quite old, it means that for some articles, you might have to scan the whole assets table, which is in fact quite expensive, or can be quite expensive. So it might be wiser in our diagram to go to the beginning and join the streams together. So not joining the tables, but the streams in Kafka in front of BigQuery to already make sense out of the data before we have to analyze it. But the problem here is, what if both streams of articles and assets are huge and endless? So in the standard streaming example, you will find a customers table, for example, and an orders table. And you say, well, customer is reasonably small, so we can keep this around, and then we're going to consume all the orders, and we're going to join in the customers. Well, that doesn't work if none of those two fits in memory. In our case, it's not possible to fit them in memory. Now you might argue, well, you could just spin up 2,500 VMs and they would fit in memory, but the problem is also that it's a cost-sensitive matter, and you always have to consume then the streams from the very beginning, meaning that Kafka needs to have the data around forever. And usually our stream processing is made or built upon the fact that the stream is only keeping 14 days of history. So that means that this is not working for us. Additionally, for your mental model of databases, BigQuery behaves like a truck. So BigQuery is very good in moving a huge amount of data reasonably fast, so in seconds up to minutes, so terabytes to petabytes up to minutes, from A to B. But what we are looking for is a Porsche. So we want something, when we want to enrich the stream of articles with the assets, we want to find one key, so the article ID, in the other stream and want to put it in. So I use the Porsche Taycan here, not because I'm a fan of it, but just I looked up the comparison right now. I think it's faster than the Tesla, so it could also be a Tesla. So if you like a Tesla, you can just imagine here a Tesla. I just want to use an electric car for environmental reasons. So what we are looking for, to come back to my picture, or is basically inside our stream processing, we want to look up, when we are consuming the article stream, each time we have an article, we want to look up the asset history for this article, and when an asset comes in, we want to also update the store, this Taycan-like store, or this very fast key value lookup store. What does it mean? Well, first, we need to ensure that assets are always processed in front of articles, so that we time shift them maybe a bit by 5 minutes, so we can make sure that if the clock time is right now 6 o'clock, that 5 minutes before 6 o'clock we shift the assets back, so we can always make sure the asset will be processed first. If there is, for example, somebody posting a new article online and there's some thunderstorm, and maybe the asset receives us before the article, so that we are sure we can update the key value store first with the 2. And then we get all the historical information plus the stuff we might just have been written. And we're going to join it into our pipeline and write it out to BigQuery as a joint table, basically. So the output table will look almost exactly like if we have joined 2 tables, but we did it in the stream processing way and writing it in the stream processing way. So then we were thinking about, okay, we know what we need. So we have a description of the car we want. So now let's look at the market and see what we can get. And we looked at different technologies. The first thing that we tried was, for example, Apache Cassandra, which is a column-oriented NoSQL store, you could say, that actually fulfills a lot of, or ticks a lot of boxes here, and we tried that. It worked, so the good news is it works. The not so nice news for us was basically we have 2 data engineers, so me and my colleague Fabian, who work in the DI team, and we don't have support from SRE. So we are completely self-dependent. So that means that if I want to go on vacation and we build something and it crashes, then either I have to fix it or he has to fix it. So what we are looking for is something that is basically managed. And we know with BigQuery that it's actually never failing most of the time. So that means that unless Google has a complete data center outage maybe in Europe, that might be a reason, but that could also happen when we have something hosted in a data center like OHV Cloud in France, which we luckily didn't host in because it burned down, as you know. So that could also happen when you host there. So that means that we're looking for a technology that suits us. And this next thing that we tried was Bigtable. And Bigtable is the same kind of thing from a management point of view. It's a bit like BigQuery because you have you have some knobs to tune, but actually it's really it's the NoSQL key value store that grows almost indefinitely, and it's something you can trust and build on, and it's almost completely managed for you. But I come to that in a moment, what you can basically, or what you have to deal with. But to fit it into a landscape for you, if you know some of these services already. So in the DI team, as I said, we have batch and stream processing things that are either sourced from Google Cloud Storage, which is something like Amazon S3 if you don't know it. It's basically a huge pool of files, and if we need to import something that has been produced in a batch process, we are getting it from Google Cloud Storage. If we have something that comes in as a stream process, we are getting it from Kafka, and then we are going to process it with Apache Beam. Apache Beam can be executed on our Flink cluster, as mentioned in the beginning, or we can also execute these pipelines in the cloud at the Google Cloud Data Flow, which is a data processing service by Google. And now to the interesting stuff. So as I said, BigQuery is columnar SQL, your standard data warehouse that speaks SQL. And Cloud Bigtable is column-oriented, so it has a schema, NoSQL. So it works by having just one primary key, and the lookup of this primary key is very, very fast. How fast? Well, it goes down to milliseconds, so it's really fast, and it also scales very, very well. The last thing, of course, here is what we're going to do with this kind of stuff. So we either process it further. So if we have it in BigQuery, we might process it further to send it to some third party, or we are processing it from Bigtable because we're reading history for an asset. Again, or we simply analyze it in Tableau, which is then displayed to business users and other things, or other people in the company that want to know what the company is doing. And we also source from Bigtable and BigQuery more intelligent stuff. So that can be going into the direction of AI platform, or things like Cloud Vision API. So to sum up this slide, it looks very complicated, I know. I just wanted to tell you that if you know some of these services, the new thing or the new kid on the block is Cloud Bigtable for us, because that's the missing part that we were looking for. Something that is like Redis, so it's a key value store, kind of, with a schema, so it's not as simple as Redis, and it is managed, and we don't have to worry about sizes or disk space. And now, as I already warmed you up a lot about how easy it is to operate it, actually the only knob you can tune when you set up a Bigtable cluster, and also after you've set up a Bigtable cluster, is this value. So you can only say, I want to edit this cluster. I'm going to say I want to have not one node, I want to have 3 nodes, I want to have 10 nodes. And this is scalability. So with no maintenance and basically nothing you have to worry about. So nothing to deploy inside of Kubernetes, nothing to worry about to manually configure, especially compared to Cassandra. So in Cassandra, you have the Cass operator that lets you deploy a Cassandra cluster, for example, in Kubernetes. There you have to then think about, okay, what happens when my provision storage is actually outgrown? How do I scale that then? And this is kind of stuff that you don't have to worry about here, because your storage grows linear also with the number of nodes. So each node can hold a certain capacity, and I come to that in a moment. But that's what I want you to remember. There's only this one knob, like a volume on a stereo, that you know. Like if you want to make it louder, you just turn it up. If you want to make it quieter, you just turn it down. Since I mentioned OHV, I hope I pronounced it correctly. So the next thing that comes to mind is, okay, what about disaster recovery? Well, since 2019, there's a blog post online on the GCP blog how you can easily create replicated clusters in distributed data centers of GCP. So in the unlikely case of burning down buildings, you can have automatic failovers to others. And this does also happen transparently behind the scenes for you. So, speaking of disaster recovery, the next question is, okay, but how easy is it to create a backup or replay a backup? So it is easy like this. You can create a schedule for your tables in Bigtable. They are basically then, so the snapshots of these tables are retained for up to 30 days. So you can, for example, have a snapshot every minute or every day in our case. And if you need to replay this backup, it lets you do that into another newly created table and asks you what this name should be. And this is super awesome, because if you have ever played around with ZFS or a file system that lets you actually restore snapshots onto other pools, or it's super awesome, because most of the time you don't want to actually roll back everything. Most of the time, or 80% of the time, you know exactly, I need this because we just deleted this and I just need this. So it lets you then create this table at this point in time with a different name. You can go there, fetch these records, insert them, and you're done. And your downtime is basically 0, because you didn't even need to stop the running table. I already said scalability is as easy as turning one knob. And to show you what I mean with that is, this is the inserting process. So basically the job that we run on Cloud Dataflow to insert the history for the assets from our BigQuery table that we had already, the 20 years of history, or almost 20 years, into our Bigtable table. So basically pre-filling our Bigtable cluster. And there you can see, so I said 30 nodes, and each node is guaranteeing you 10,000 requests per second. And here you can see nicely that we could insert 300,000 elements per second. And after, I think, 1 hour, I was done. And this is also giving you peace of mind, of course, because if you know that you can disaster recover the complete history in the playback in 1 hour, that's super nice, because then you're starting to experiment. You're thinking about, well, we did a mistake here, we should have designed it differently. And you end up in these situations. And most of the time you're saying, yeah, but now it's too complicated to change, so we're just going to keep it. In this situation, you can just say, oh, whatever, we're just going to change it because we found out it's better now, so we fix it. And if you don't take my word for it, this is my colleague writing to me in Slack, after I set up the cluster and set up the first use case, we had another use case with Zendesk tickets, where we wanted to link Zendesk tickets with customer information. Another use case of we want to do a point query. So we want to fetch information for this ID and this ID only. And this is where BigQuery is not the best one, because BigQuery can analyze huge data sets. So basically over a set of data, but here you want to fetch a particular point. Again, this is a Porsche example where you're just driving one person. And he was basically also launching a pipeline not in Java, which I was using for the Beam SDK, but in Python. Then inserting the history into Bigtable. And he was also using the emulator. What is the emulator? We will come to that in a couple of minutes, because you might be interested in, okay, how can I give this whole thing a spin? But let me first show you what I said before about the ease of pushing data around. So if you want to, again, if you want to read something from BigQuery and you want to push it into Bigtable, the fastest thing you can use is Cloud Dataflow, a service by Google that is spinning up machines behind the scenes for you, executing your pipeline, and then inserting this into Bigtable here. And it scales linearly together with the Bigtable nodes. So for example, we had 30 machines executing this code, spin up by the Dataflow service. We spun up or we scaled the Bigtable cluster to 30 nodes. And then this was executing, giving you this nice graph of saying how much, or how far it got done. And after it's done, basically Dataflow is shutting down and you can scale down the Bigtable nodes. I had a quick chat with the product manager of Bigtable after some discussions with our GCP representatives, and he told me that maybe even the scaling will maybe in the future will be more automatic. But that's, as I said, this is the only knob you can right now tune or need to tune. But again, it's just one knob, so I don't. It's not a huge issue to do that. And again, this kind of pipeline you can express right now in Python, Java, and Go, which is basically the Dataflow or the Beam SDK languages. But of course, for Bigtable itself, there are client libraries in any language you can think of. So JavaScript, Node.js, C# and others. So if you want to program against Bigtable directly, all the libraries are already available. Now to my main caveat. So to make the whole system very fast, you need to think about your schema design, because you are, with your schema, as I said, you only have one primary key. So you need to be sure that the primary key has two very important functions in this case. It needs to make sure that your data is distributed evenly when you're writing the data, and it should be enough to fetch as little data as possible. So for example, I give you an example. When you start out with using Bigtable, you might use your customer table. Your customer ID might be a number that is going from 0 and then upper, like a counter in a relational database system. The problem with that is that if you have 3 Bigtable nodes, and they go from, let's say, for example, your indices or the Bigtable ring goes from 0 to 100. Then the first node of Bigtable will be responsible for everything that starts from 0 with 33, the next one from 34 to 66, and the next one from 64 to 100. So now if you start inserting into Bigtable with a lot of pressure, most of your customers will go atomically, or not atomically, but increasingly from 0, 1, 12, everything will hit the same node in Bigtable. So we will have a hot node basically. The nice thing with Bigtable is that you have this super awesome web interface that actually gives you an idea of at what point in time how hot was your row key. So if this is actually evenly light up, even bright, then you have a very nice row key. If you did a mistake like I did in the beginning, you have only a tiny fraction here, very, very hot, and that means actually that your row key is not evenly. So of course, we are in Switzerland, so it's not like super huge mega data, but still we have 4 million people on our platform, so it's something. So you want to make sure that this is not sequential. and to avoid these hotspots, basically. And the last big enlightenment I had was basically that tables are 3D. That took me, I think I read a blog post, and that was actually like, this changed everything, because before I was like, hey, how can I design my row key and so on. Any particular value in Bigtable is identified by its row key, including the column family and the cell timestamp. What is a column family? Not really important for today's talk, because that actually lets you group different columns in a table again to fetch only a certain column family. So forget about this, but just remember you have the row key, you have the column key, so like a normal table, but also timestamp. That means that your cell values can have history. So you can fetch a value for an article, in our example, an asset, a description for an article on the 1st of January or on the 2nd of May, because that's basically the third dimension that comes into play here. So now the last question I have in mind actually that comes up when you think about this pipeline. So again, you're reading from Kafka. You have assets always processed first because you have this temporal ordering. You write out the asset that you receive, you fetch all the assets, and then you join in the articles because you actually looked up for an article all the assets, so by ArticleID. And why does this work? Well, Bigtable has read your writes consistency. So if you have a writing thread, and you are making sure that each thread is responsible in your application for handling, so the same custom ID is always handled by the same thread, for example, so it's not spread out, then you have the guarantee that you read your own writes. And this way we can make sure that if we write out something and then later 1 millisecond later we fetch everything for this article ID, then we know that our own writes will be inside of this fetch, because otherwise you would not have this. So this is also very important. So read your writes consistency saves us in this scenario. So what I want you to take away from my talk is that where BigQuery allows you to quickly analyze terabytes to petabytes of data with SQL, basically, Bigtable lets you do NoSQL key value lookups in milliseconds. And these key value setups, so the value can be a fully fledged schema-based table. And Bigtable is very easy to operate. It requires basically no maintenance, no software upgrades, and no security fixes. There's just one knob to tune, so scaling is very easy. The only thing that you can scale is the number of instances. And that's it. And with that, I want to say thank you for your attention. And of course, I have the hiring slide here. So we are looking for collaborative co-workers. You can check out our jobs on our jobs page. And we are looking especially for Valbon in our French office. But also in Zug, there are some positions open. So go and check them out. Here are my sources. So because all the images I took, these nice ones, of course, I have to give credit to the people that actually took them. And I'm open for any first questions that might have come up so far, because maybe I've spoken too fast. Is there anything from the internet? Are confused or maybe want to know something?
Yes, there's a question from Pierre. He wants to know which connector did you use from Beam-Flink to Bigtable?
So Apache Beam has the Bigtable I/O. That so we use Java, the Java SDK of Beam, and Beam has the Bigtable I/O built in. The good thing is that Beam or Apache Beam is the open source data flow SDK, so all the Google services are more or less covered very well, and so all the connectors there are mostly feature complete. Does this answer the question, or?
He may ask again in the chat if it doesn't. And he wanted to know another thing. At the end of the talk, he asked Java or Python I don't know if you can relate that to the exact.
So we use Bigtable with Python libraries for the service with Zendesk for reading and writing. We also have Beam pipelines in Python to fill Bigtable, and we use Java pipelines to fill Bigtable and connect to it, and we use Java for BigQuery. So Java and Python is both. So data engineering, I would say 80% Java, and for everything else, it's more 80% Python. So if you move out of data engineering, where it's just Kafka to BigQuery, for example, then it might go more into the Python direction. But in our team, it's Python is the main language as soon as data engineers talk to analysts and other people. So that's why we have both.
Okay, and then he wanted to know again. So no Python connector yet.
For Bigtable, there should be one.
Okay.
I would say, so for Beam, I'm 99% certain that there is a connector for Python. Actually, I'm 99.9%, but I can check after the talk. For normal client libraries, I can show you in a moment that there is a connector. I prepared actually, if there is not an urgent question right now, I prepared this additional slide because most people then are interested in, well, BigQuery I pay per volume, so it's like pay per use, like your phone when you have a prepaid card, which is actually not prepaid, but you get the idea. And with Bigtable you have like real costs, and but the good thing is, compared to Cassandra, where you need to start with at least 3 nodes, that was also my wrong assumption in the beginning. With Bigtable you don't need 3 nodes. You can live with only 1 node. Of course, it means that sometimes it could happen that the node becomes unavailable. It never happened to us, but in our data processing and in our pipelines, we have retries. So even when the node becomes 1 second unavailable, we can deal with that. If we are not able to deal with that, we could spin it up to 2 nodes. I'm just making up here the example because we're running our stuff in Belgium, so Belgium is a bit more expensive. You can see that in Belgium it's $468 per node. That's the linear cost if you scale with 1 or 2 or 3 or 4 or 5 nodes. You get you can assign up to 2.5 terabytes of SSD storage for the node, and 7.5 terabytes of storage if it's an HDD node. So that's basically what you maximally can put on 1 node. If you add another node, that grows linearly again. And each node, as I already said, can handle up to 10, can guarantee 10,000 requests per second. So that gives you peace of mind when you're really planning this kind of stuff. You can see here, which is very tiny, I'm sorry, but this is actually telling you, so I told you in the beginning we have huge data, and here it's saying that we have only 269 gigabytes stored. And that is because it's compressed. So the nice thing with Bigtable compared to BigQuery is, for example, when you take the same table one-to-one from BigQuery and you push it into Bigtable, because Bigtable has also data types and so on. If you have string types, for example, descriptions of articles are, of course, huge strings. The compression, when it kicks in, is really nice and actually can compress it a lot. So this raw data here was around, I think, 600 something, and this is now 269 gigabytes. So compared to the table in BigQuery, this is really not as much as I also had anticipated, because when I did the back of the envelope calculation, I looked at how much storage do we use in BigQuery. Okay, around about this I should plan for Bigtable, but no, it's actually less because you get compression, which is super nice. And I have another bonus slide. So because it may be a bit fast when I talked about the join between articles and assets in Kafka that went into this pipeline. The reason why it works is because the framework, or the Beam framework, actually gives you guarantees as a developer. And when you use a windowing function in Beam and you have these timestamps attached, you can make sure that all events that are within a certain time frame, the stream of events is sliced up, and all these events are processed together. So if you slice up the time by 1 hour, out of order events are automatically ordered, and you can make sure that all events that happen between 4 o'clock and 5 o'clock are all within this window. And then if we rewind the assets by 5 minutes, we can make sure that if we then send them down to this enrich function, which first inserts all assets into Bigtable and then fetches all assets for a certain article ID, that this is actually including everything, as long as our pipeline is not 5 minutes behind. But this is actually to prove you that this real magic, or this that this is actually working, is due to the fact that the Beam framework gives you this windowing transform and lets you write it like this. And now I also prepared a quick demo. I hope it will work. So because there was a question from the audience about connectors. Again, for Beam Python, Bigtable should be available now, but I will I stand corrected if this is not the case. I just have to quickly fix my display because I cannot see it. But what I want to show you now is basically the... I know why. What I want to show you now is that with the standard library that comes with the Python SDK from Bigtable, you can already, with a few lines of code, start doing things. And of course, you saw the costs, so most of the people will be scared and say, yeah, but how can I start coding with something? I mean, before I get something out of the door, a prototype that I can show my management to, actually justify these costs, I already have spent so much money, I will never get the approval, because sometimes, you need to get the working prototype first before you get the approval to do the prototype, sometimes. So the good thing is that the G-Cloud SDK comes with the Bigtable emulator that lets you write in your favorite language with the client libraries against a Bigtable emulated thing on your local machine. And that is also working for testing and other things. So if you use CI, you can use that to actually test that your application is doing the right stuff. So here I have on my screen, is it big enough? Yeah, okay. So the top of my screen here is the Cloud Bigtable emulator. I've executed this with this command locally. And below that I have just a normal command line. So here I have the CBT command line utility that can connect to my Bigtable local cluster, and I've created this meetup table. So right now, when I read this table, it's empty. And read is something you should never run on a production cluster because it actually reads everything. So if you have a huge table, it will just stream that back to your machine. And if you are on a data plan and you use UMTS, you are screwed. So this is actually the code. This is all that needed to actually insert something into Bigtable. So this is just the function to get the timestamp in Python. The column family, there's again, if you don't want to use column families to group your data, the default is always use CF1 as a column family name, because that's the default in all the libraries I've seen. So not really interesting. Here's the row key. In my example here, I have 431, so I reversed the key already for you. And there's a direct row transform. And this direct row transform basically writes the row out directly. You can also chain up your transforms to make it do everything at once. So if you want to make sure that many transforms, because there's no transactional concept, right? And here we have the function. So we set the username of this column family for this timestamp to Alice, and then we just run the commit. And that's everything you need to do to write out the value. So I'm doing this now. It has been executed, and now if I read the meetup table, I can see that here, this is how actually it's displayed. If you would also connect to a production cluster, you would see the row key first, you would see the CF1 as a column family, and then you would see all the columns that have been defined, and then their values. And here we see the timestamp. And to give you the 3D concept again, if I just execute the same again, because then it will use the current timestamp, we see we have 2 times the value, and here there's a difference between the 2 timestamps. So if this username, for example, would have changed over time and it would have written Bob, then I could be then retrieving this this key and this row key and this column for this specific timestamp in a filtering this client. Yeah, and this actually is everything you need to know to get started with Bigtable. So I can just encourage you to try out the Bigtable emulator on your local machine, so you don't need to spin up a whole cluster. And you can start building applications with it. And if you have any more questions, I don't have any more slides or demos for you. So now you are free if you have any more questions for me regarding my talk. Thanks.
Thank you very much, Tobias. We have no more questions left, so the two people are talking to each other in the chat regarding this link where this connector is. So
this is the best audience that is actually helping each other.
Okay, also thank you very much for your talk. So, and we'll hand over now to Nick. Give us 2 or 3 minutes to connect his notebook, and then we'll be right back with Sebastian Nickel.